Okay, this is lecture 5.7, factoring by special products. So basically, we're going to learn some shortcut factorizations that we can obtain by memorization of a few formulas. The factorization techniques that I showed you last time always work, and they work in this case too, but many times it's much easier to factor special types of polynomials that were introduced by doing the reverse of the special products that we learned, I think, 2 lectures ago. So let's use our regular factoring method and factor x squared plus 10x plus 25. So again, as usual, we can make our little table. It doesn't have to be very formal. Well, again, it's Saturday and raining outside. So we have x squared, then we put our constant term, and then we put our degree 1 term. So since this is x squared, it's a monic polynomial. I have x and x, those are my only choices. Now 25 is, there's only really 25 is equal to 1 times 25. That's one factorization, and it's negative. And of course 5 times 5. So I'm going to put 5 here and 5 here. That's going to give me 5x plus 5x, and that gives me 10x. 5 times 5 is 25. X times x is x squared. So I get my factorization as x plus 5 times x plus 5. But this is just the same factor multiplied by itself, so we commonly write that as x plus 5 squared. Because remember, b times b is equal to b squared, and in this case, this is some value b, and that's the exact same value b, so that's x plus 5 squared. So let's try to factor x squared minus 36. And I give you a hint for this one. So we're going to write x squared minus 36, using the hint, is x squared minus 0 times x minus 36. Again, we're going to do the same exact trick as before. This always works, like I said, if whatever factorization method that we're given will always work, provided that the polynomial is not prime. We'll get a factorization. So again, this is a monic polynomial. So I've got to take, it's not working. There, I got it. So I have x squared up here, then minus 36 here, and 0x here. So again, that's going to be x times x, and minus 36 is equal to, well, minus 1 times 36, or for that matter, 1 times minus 36, or it's equal to minus 6 times 6, or 6 times minus 6. So I'm kind of thinking that we should do these. So let's put minus 6 times 6 there. So that gives me minus 6x plus 6x, and indeed they add up to 0. So my factorization is x plus 6 times x minus 6. So I'm hoping in both cases you recognize something. This is a formula we had before. A plus b, a minus b is equal to a squared minus b squared. In this case, x plus 6 times x minus 6 is x squared minus 6 squared, which is exactly what we have, because x squared minus 0x. The 0x I just put in there because we need a middle term for this process. So here is our special factorization forms, and really that's all we're going to be reviewing. Is given some expression A and another expression B. Many times this is an x and this is just a constant, but it could be 2x or 4x, whatever. Then a plus b squared is a squared plus what's in parentheses multiplied by each other, a times b, then multiplied by 2 plus b squared. Again, a squared at the front, b squared at the end. A times minus b is minus ab. Multiply it by 2, get minus 2ab. And here's the one that is, I think, just absolutely essential that you memorize. A plus b times a minus b is a squared minus b squared. So what we're going to be doing is, the last time when we were first introduced to these, we were going in one direction. And that's the thing about math. We always go in both directions. So we were given what was on the right-hand side, and we produced what was on the, we were given what was on the left-hand side, and we were asked to produce what's on the right-hand side. And now we're going to be given what's on the right-hand side and see if we can produce what's on the left-hand side. And there's some pretty easy checks. So what we'll do is, for a perfect square trinomial, I will give you some checks for so when we're doing a trinomial that has 3 terms, the middle term is non-zero, so it has 3 terms. So x squared plus 16x plus 64. So this is what we want to do. Ask one question. Is the first term, which is, by that I mean the degree 2 term, a perfect square? And by a perfect square we just mean some expression a squared, or some expression a times b squared. So that's the first question. I'll put a little box here. Then the second question we ask is the constant term also a perfect square? And if it is, we might have a perfect square trinomial. And then is the middle term, degree, which is our degree 1 term in this case, the product of, let me get more room up here, the square root of the first degree 2 term times the square root of the constant term times 2. So if the first term is a perfect square, then its square root is a single term. And remember, we're always taking the positive here. If the last term, the constant term, is also a perfect square, then its square root again is just, I can just remove it out of the radical. So let's look at this. My first term is x squared. So it is a perfect square. and the square root of x squared is equal to x. Is the constant term also a perfect square? Yes, because 64 is equal to 8 times 8, or in other words, the square root of 64 is equal to 8. So now, my last question, if I now look at these two things that I've extracted, my x and my 8, is the middle term equal to 2 times 8 times x? And that's equal to 16x, and it is. So I've got check marks in all three of these. So that means this is a perfect square trinomial. And all I put in here is my x term and my 8 term, and I square it. So let's do that again. Except I'm not going to write those down. We're just going to use them. So here we go. X squared minus 18x plus 81. So is the square root of x squared? Well, that is actually x. That's easy. What's the square root of 81? Well, that's 9. So my first two criteria have been checked. So now we have to add one little thing. We have to check if the middle term is plus or minus 2 times 9 times x. And indeed, this is plus or minus 18x, and my middle term is the minus 18x. So what it is indeed a perfect square trinomial. So I put my x term here, and the square root of my constant term here, and it's going to be squared, but since it's a negative, I put a negative there. That's x minus 9 squared. Let's do another one. So let's take the square root of my degree 2 term. That's going to be x. Let's take the square root of my constant term, and that's 7. Now, if this were not a whole number 7, or you'll see in just a second we'll get some constant terms that are like 2x squared, then the square root of 2x squared would be the square root of 2x. So the coefficient here is a whole number. This is a whole number. So now I check plus or minus. You always add the 2. That's the big thing you can't forget. 2 times the constant term, the square root of the constant term, times the square root of the middle term. So plus or minus 14x. Well, our middle term is plus 14x. So again, my factorization is x. Since it's a plus, I grab the plus sign and the 7, and don't forget the squared. So what I'm saying is x squared plus 14x plus 49 is equal to this. So this is a factorization. Don't forget that either, because x plus 7 squared is equal to x plus 7 times x plus 7. So now we're going to move to another case. So the only time that perfect square binomials, a factorization can be a perfect squared binomial, is if we have actually three terms, 1, 2, and 3. Here we have 3 terms, 3 terms, 3 terms. Now suddenly we only have 2 terms, and the middle term, 2 terms separated by a minus. So when we have 2 terms separated by a minus, we've got a different rule. So what we do here is, I've got 2 terms, so the only possibility this could be is the difference of perfect squares. So this is easier. I take the square root of x squared, and that's x. And then you just take the square root of just the positive value, because this always, let me write that in there, must be a minus. If it were a plus, then you can't do anything. This doesn't work. It has to be a minus sign. So you take the square root of 49, and that's equal to 7. So that's the coefficient of x is a whole number, and that's a whole number. So this is equal to x plus 7 times x minus 7. So this is not a squared. These two factors differ by a minus sign. But this gives you the value of the 2 components in the factorization. Then you just alter the minus signs. And again, it's exactly the same as x minus 7 times x plus 7. There is no preference in where you put the minus sign and where you put the plus sign. So here is going to be an interesting one. And let's take a look at this one. 50 minus 8y squared. Well, the square root of 50 is 5 on the square root of 2, because the square root of 50 is equal to the square root of 2 times 25. And since 25 is a perfect square, I can move it out. So that's not a perfect square. That doesn't count. But there is this little trick that we always have to remind ourselves. And here is the reminder. Always first factor out any or the GCF of both terms. So, okay. Well, both terms don't share a y, so y is not going to be in the GCF. But 50 and 8 are both divisible by 2. Is 50 divisible by 4? No. So the GCF of 50 and 8, remember, we know it's going to be less than or equal to 8, but greater than or equal to 1. So 50 is equal to 2 times 25, which is 5 times 5. So 50 is equal to 2 times 5 squared, and 8 is equal to 2 times 4 times 2 times 2. So 8 is equal to 2 cubed. So notice the only common factor they share at all are the 2's. And of those 2's, we take the 2 with the smallest exponent. And that's this one right there. It has an exponent of 1. So let's factor out a 2. So 50 divided by 2 is 25. And minus 8y squared divided by 2 is minus 4y squared. So now the question is, can I do anything else? So I have factored it. I pulled out a non-trivial greatest common factor. Well, what is the square root of 25? It's equal to 5. What is the square root of 4y squared. Well, it helps to realize that 4 is 2 squared y squared. So this is equal to the square root of 2y squared. So since that's the product of two factors squared, I can literally just remove the square root, so that's equal to 2y. So the radical sign has disappeared. So as it turns out, this is the product of 5 minus 2y times 5 plus 2y. So again, let's observe 25 minus 4y squared doesn't have a middle term, and the two terms that it does have is separated by a negative, so it's a candidate for the difference of squares factorization. So here's another one, so I'm going to have to amend what I said before. All we care is that something is a perfect square. It doesn't have to be an integer. So again, we have x squared minus 1/4. So again, the only possibility here is a perfect square, the difference of perfect squares. So let's take the square root of x squared, and that leaves us an x, so that's good. The second one's going to get you, what's the square root of 1/4? Well, by certain rules, quotient rule, that's the square root of 1 divided by the square root of 4. Well, the square root of 1 is just 1, but the square root of 4 is 1/2. So the point is that the radical sign has been completely removed, and that's all we need. So this is x minus 1/2 times x plus 1/2. So x squared minus 1/4 is equal to that, and that's a non-trivial factorization. Okay, this is another really good example. So they're starting to play with things. Again, this looks really different, but abstractly, it's not. So here is the first mistake students will make. They will expand x minus 3 squared into x squared minus 6x squared plus 6x plus 9 minus 36. And they will simplify and they won't get anywhere. All you have to remember is literally this is something squared minus something else squared. So what is the square root of x plus 3 squared? Oh, it's just x plus 3. What is the square root of 36? Oh, that's just 6. So this has the following factorization. X plus 3 squared minus 36 is equal to x plus 3 minus 6 times x plus 3 plus 6. Now we can do some simplification here. X plus 3 minus 6 is x minus 3. And x plus 3 plus 6 is x plus 9. Now, if you were to have expanded that to x squared plus 6x plus 9, and then subtracted 36, you would get x squared plus 6x minus t. That would be 27. Yeah, 27. So you can factor that. Let's go ahead and factor that. Using the other way, see how much longer it's going to take? But let's do it, because we've already started down that road. X squared minus 27, 6x. So that has to be x. That has to be x. So what two things multiplied together gives me minus 27? Well, minus 3 and 9. So that's minus 3x plus 9x. And that gives me 6x. And literally, I still get the exact same factorization as I did before. X plus 9 times x minus 3, which is exactly the same as I get here. The factors are reordered, it doesn't matter. But wasn't this a lot faster? I think so. And p to the fourth minus 16. This is a good one as well. So p to the fourth minus 16. So we come over here, and what's the square root of p to the fourth? Well, that's p to the 4 divided by 2, which is p squared. What's the square root of 16? Well, that's equal to 4. So the radical sign has completely disappeared. So this is equal to p squared minus 4 times p squared plus 4. So those are some great uses of difference of squares. Now this last one is forms involving cubes. There are special factorizations of cubes, and you have to more or less memorize these. So a cubed plus b cubed is equal to a plus b times a squared minus ab plus b squared. So this part right here is almost like difference, almost like a perfect square, but there's no factor of 2 in there. It's not a squared minus 2ab plus b squared. And the minus there is rather surprising because you have a plus there. And then a cubed minus b cubed is a minus b times a squared plus ab plus b squared. Now, this is an important factorization in trig. It's apparently used all the time. I don't think I really used this, or may have not even been introduced to it since I started back in math late in life, until I was taking graduate level classes. But we're going to go ahead and introduce them to you here, just so you'll be aware of their existence. And if you ever encounter them again, you will know where to find the factorization. So x cubed plus 8. So here's what I'm saying here. You won't find these on the exam, but you probably will find them in the homework. So it's a good idea to memorize the following cubes. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and 5 cubed is 125. So we're going to rewrite this as x cubed plus 2 cubed. So there I have a sum of 2 cubes. So its factorization is x plus 2 times x squared minus 2x plus 2 squared, which is equal to x plus 2 times x squared minus 2x plus 4. So let's do that again. Let me go a little bit slower here. So x squared plus x cubed plus 2 cubed. So underneath, let's write my formula. A cubed plus b cubed is equal to a plus b times a squared minus a times b plus b squared. So this is my guide. Even when you have it memorized, sometimes you don't know what to do. So let's use that guide. And I will note that my A is equal to x and my B is equal to 2. So that's equal to A plus B, x plus 2, times A squared, that's x squared, minus A times B. So A times B is x times 2, but we normally always put the coefficient in first. So instead of writing x times 2, let's write 2 times x. And then plus b squared is 2 squared, which is 4. So doing that same method will get you the factorization for p cubed plus 27. Let's just do the y cubed minus 64, just so you'll have an example. And that's it. So again, let's have our paradigm, our rule, our guide, whatever you want to call it. Our guide. Our guide comes from the formula. No, I don't want you to memorize the formula for the difference of cubes. Factorization. So we have a minus b times a squared plus ab plus b squared. So the middle sign here, the plus, is always different from the sign here, and the sign between the binomial term is always the same as this one. So we're given y squared minus 64. But remember, 64 is equal to 4 cubed. So I'm going to erase my 64, and I'm going to add in the knowledge that 64 is 4 cubed. So if you need to down here, you can identify your a, which is y, and your b, which is 4. So that's equal to y minus 4 times y squared plus a times b, which is y times 4, but we're going to write 4 times y, because we always put the coefficient in front, plus our b squared, and b is 4, and 4 squared is 16. And let's actually, before I leave here, let's verify that this formula is actually correct. And I think that's the end for 5.7. It's a really short lecture. And right here is on the last page, it's also just basically copied and pasted from your book, is a whole layout of how to factor special products. But I want to go ahead and let's verify this. Let's actually show, because it's a good review, we want to show that y minus b times y squared plus 4y plus 16 is indeed equal to, that's supposed to be a 3 there, a y cubed minus 4 cubed. Sorry. I'm glad I went back and I saw that. Well, this is how we're going to do it. Y times y squared plus 4y plus 16 minus b. My b is a 4. I'm really flubbing this one up. It says my b is a 4 right there. So this is a good exercise. So again, we're just using distribution, and then we'll be simplifying terms. So y times y squared is y cubed. Y times 4y is plus 4y squared. Y times 16 is plus 16y. Minus 4 times y squared minus 16y minus 4 times 16 is 64. So let's collect like terms. Here's my y cubed term. Now let's do my squared terms. So that's 4y squared. Is there another squared term? Yes. A minus 4y squared right there. Now let's do our degree 1 terms. 16y right there. And minus 16y right there. And then my constant term. And finally, we simplify. Here are my like terms and my like terms. So I have y cubed. 4y squared minus 4y squared is 0, so these cancel. 16y minus 16y cancels. So it's y cubed minus 64, which is the same thing as y cubed minus 4 cubed. Okay, that's it for lecture 5.7.